So in parts 5 and 6, what we want to do is take that resultant vector that we determined in part 3 and 4 and convert it back to polar form. So the way that you do that for here, if you notice part 5, you're asked to do it by hand. So I think the easiest thing to do is take whatever values you obtain for the resultant vector when you add it together, V3 and V4, and just plot it in the plane. As long as it's in the first or the fourth quadrant, you're able to use these formulas directly, namely the magnitude of the resultant vector you're just going to get by Pythagorean's theorem. It's equal to the square root of the x component squared plus the y component squared. And this approach works for wherever your vector is at, whether it's in the first, second, third, or fourth quadrant. And you can kind of see what's going on here. Here is the resultant vector. It has a positive x component of 4.12, a positive y component of 2.12. So it's going to be up here in the first quadrant. This magnitude that we're trying to find is just the length of the vector here. And the length of the vector, as we discussed in lecture, if you were to envision dropping a perpendicular to the positive x-axis, it's just going to be the hypotenuse of a right triangle where the two bases have side lengths corresponding to the x and y component. So there's my x component, there's my y component. If I square both and take the square root, that will give me the magnitude of the resultant vector, which is just the hypotenuse of that triangle. And in order to get the angle of this vector, that's that angle that's right inside here, notice that the tangent of that angle is equal to the opposite side length divided by the adjacent, 2.12 divided by 4.12 approximately. I've rounded, of course. So in order to get the angle, you need to take the inverse tangent function of that ratio. So those are the two computations that I need to make for part 5, kind of doing it by hand. And I'm just going to use MATLAB as a calculator here. So I keep opening the web app of MATLAB. Sorry about that. So I'm going to take square root of 4.12. The square root function is SQRT in MATLAB. Take your first value that you're squaring, write it, and then use the actual caret key, which you can get as it's over your 6 key, so shift 6. And then take the y component and square it, and then close the square root function. And you'll get 4.6334. I'm going to follow the same convention we have and just round that to 3 significant figures. I'll show you on the dot cam. I wrote it in the wrong place, unfortunately. But the way that you compute the inverse tangent is to take a tan b of, again, the y component, 2.12, divided by 4.12. This is a function that's built into MATLAB, so it knows the name. You just pass the arguments into the actual within parentheses here. So when you do that, you get 27.2 degrees. So we can look at our .cam and just see if that is a reasonable value. And this is larger in X than it is in Y. So the angle is going to be less than 45. So 27.2 is a reasonable angle. And that distance, 4.63, is reasonable as well. So the last thing that we want to do, that is part, here we go. I'm going to open back up the script, part 5. So you'd want to include your results for doing it by hand right there. And then we want to verify our results from part 5 in MATLAB. Then we're told to use the cart-to-pole function. So let's actually see how that works. So the easiest way to see how something works is to actually type help and then the name of the function afterwards. You can also just go to Google as well. That works, but sometimes you can kind of just see through the examples, how this actually works. This particular help file doesn't have a lot of examples, so we can just go here in the top, and we can see that if we read all this, all that we need to do is use the function cart-to-pole, pass in the x and y coordinates of the vector, and then we're going to get back the angle and magnitude of the vector as arguments. So I always just copy the code that's provided to me in the help file, and I'm going to put a new comment to say what I'm doing here is to convert the resultant vector back to polar form. And then I'm going to substitute in what is the resultant vector, what is the x component? Well, it's just VR1. The y component is VR2. Remember, back to the last video, the resultant vector is stored in this vector VR. X component is the first element, y component is the second element. So what VR parentheses 1 is doing is grabbing that first component, which is the x component. VR parentheses 2 is grabbing the second component, which is the y component. So notice if you run this, and I'll just run that line of code, I get a magnitude of 4.6352, which within rounding error is equivalent to what we got doing it by hand. However, the angle that I get, 0.4754, it looks a little bit off. And if you go back and you read this help file, what you will notice is that the angle that carte de pole returns by default is the actual angle in radians. And I think we can see it somewhere here. Sometimes it's buried down a little bit in the actual documentation. But I don't want to hold you up while you're watching this video, but notice that if, and CLC just clears the command window, if you take that value that you computed, TH, which is the actual angle, and you convert it manually to degrees by multiplying by 180 divided by pi, that you will get, we remember that MATLAB, the variables are case sensitive, so we stored ours in TH, and we'll change the name of that variable to make it more readable in a minute. But notice if I do a conversion from radians to degrees there, then I get 27.2, which is the same value that we determined by hand using that inverse tangent approach. So in terms of what you'd like to turn in here, I would change the name of TH to angle VR rads, and I would just make this mag VR, and then I would do a conversion of, to get angle VR, I'd take angle VR rads and multiply by 180 divided by pi. And I believe we've talked about it before in the course, but pi is actually a built-in constant into MATLAB, so you don't have to type 3.14. So notice if I run my entire script now, that what I get is the magnitude and the angle. So in terms of what you're turning in, I would just take a screenshot of the result from the command window, and I would paste this code into, because it says to do it in MATLAB here. So I would show how that computation looks. I would take a screenshot of the actual result from the command window and include it as well. So maybe, and I can trust you that even if I can't see the entire thing, that's how you obtain those values. Sometimes if you use Paint and take screenshots, for those of you that are doing it that way, what you will find is that you overwrite a little bit and it's hard to see. So in those cases, if you ever don't think you've captured your full screenshot, just close Paint and reopen it. But there is the process of doing it in MATLAB, and you'd have your by hand work here. So all that you need to turn in is these calculations that I just did for V1 and V2 for V3 and V4. And you should find that it's not too bad of an approach. But if you have any questions, feel free to reach out to me, and I will. Good luck, and I'll talk to you all soon.